In this video, we will see how to completely factorize some special types of polynomials. Let's start by linear polynomials, and we know that these are already completely factorized, and it doesn't matter if we are speaking over the reals, or over the complex, or over the rationals. And for quadratic polynomials, we know that if they are reducible, then they have to be products of linear factors. So they are going to be reducible over rationals, reals, or complex numbers, if and only if they have a root in the rationals, reals, or complex numbers respectively. So linear and quadratic are easy. So for example here for quadratic polynomials, if f of x is x squared minus 2, then it's not reducible over the rationals as it doesn't have a rational root, but it is reducible over the reals and complex numbers. So its complete factorization over the real and complex numbers is x minus square root of 2 times x plus square root of 2. So the only thing we need to be able to do in order to find the complete factorizations of quadratic polynomials is to be able to find the roots. And we do this either just by inspection or by using the quadratic formula. For example, for the polynomial x squared plus 2x minus 3, if we observe that 1 is a root, then we can immediately find its complete factorization over rationals, reals, complex numbers, and it's x minus 1 times x plus 3. The quickest way to find this other factor is to observe that if we have the polynomial x squared plus ax plus b, and if it factorizes as x minus x1 times x minus x2, then the sum of the two roots is equal to minus a, and the product of the two roots is equal to b. So if we know one of the two roots, then we can use any of these two formulas to find the other root. A very important point here is that we need to take care when using the quadratic formula with a complex but not real polynomial. So it's not easy as it first sounds. So let's suppose we want to completely factorize the polynomial x squared plus 2x plus I over the complex numbers. So if we blindly apply the quadratic formula, we will get that the roots of f are minus 2 plus or minus square root of 4 minus 4i over 2. But then we have a problem in that we don't know what the square root of 4 minus 4i means. So what it should mean is that the roots of f are minus 2 plus z over 2 and minus 2 minus z over 2, where z is a complex number whose square is equal to 4 minus 4i. But we need to determine z. To do this, we begin by writing z squared, which is equal to 4 minus 4i, in the form r e to the I theta, i.e. r cos theta plus I sin theta. And then we can take z to be equal to the square root of r times e to the I theta over 2, i.e. square root of r times cos theta over 2 plus I sin theta over 2. Okay, to determine r is equal to the square root of 4 squared plus 4 squared, which is equal to 4 square root of 2 in this case. And for cos theta and sin theta, if we go back to the definition of z squared, we know that r cos theta is equal to 4, and we have determined r, so cos theta is equal to 4 divided by r, which is square root of 2 over 2, and similarly we determine sin theta, which is equal to minus square root of 2 over 2. But what we need is not cos theta and sin theta, what we need is cos theta over 2 and sin theta over 2. And to determine cos theta over 2 and sin theta over 2, we use the half-Allegor formulas. That cos square of theta over 2 is equal to 1 plus cos theta all divided by 2, and sin square of theta over 2 is 1 minus cos theta all divided by 2. So after we do the calculations, we can determine cos square of theta over 2 and sin square of theta over 2. But of course we need the cosine and the sine, not their squares. So what it remains is to decide on the sines of the cosine and the sine of theta over 2. Now since the sine of theta is equal to 2 times the cosine of theta over 2 times the sine of theta over 2, and since we know that the sine of theta is negative, we determined it to be minus square root of 2 over 2, and so we know that one of the cosine theta over 2 and sine theta over 2 is positive and the other is negative. And actually it doesn't matter which choice we make, as this will only affect the sign of z. So we can, for example, take cosine to be positive, sine to be negative, and so we have an expression for z, which can be simplified after a few calculations. And so finally, x1 is going to be 2 plus z over 2, x2 is going to be 2 minus z over 2, and after the calculations, it can be these expressions can be determined. And of course, the complete factorization is x squared plus 2x of x squared plus 2x plus I is x minus x1 times x minus x2, where x1 and x2 are these two expressions. Okay, so let's move on to cubic polynomials. Over the real and complex numbers, we already know that cubic polynomials are reducible. As already mentioned, there is a cubic formula for determining the roots of a cubic polynomial and therefore its complete factorization, but we will not discuss it here. So instead, we will only see some special cases in which we can determine the roots by other methods. And in particular, we will discuss cases in which the polynomial is also reducible over the rationals. Now, if a cubic polynomial is reducible over the rationals, then we can write it as a product of two non-constant rational polynomials. And since the sum of the degrees of these two polynomials must be equal to 3, one of these polynomials must be a linear polynomial and the other one must be a quadratic polynomial. So, a cubic rational polynomial is reducible if and only if it has a linear factor, and this happens if and only if it has a rational root. And whether a cubic polynomial has a rational root can be determined by the following theorem, which is known as the rational root test. This test says the following. Suppose we have a polynomial with integer coefficient of the following form: a0 plus a1x plus ... plus an x to the n. Then the rational root test says that if f has a rational root of the form p over q, where the greatest common divisor of p and q is equal to 1, then it must be the case that p, the numerator, divides a0, and q, the denominator, divides an. So for example, suppose we have the rational polynomial x cubed plus 7x squared over 2 minus x minus 1 over 2. So as it is, the rational root test does not apply to this polynomial because its coefficients are not integers, but we can rewrite this polynomial f of x as 1/2 times g of x, where g of x is a polynomial with integer coefficients, and which is the one that we seek to completely factorize over the rationals. Now the rational root test applies, and it says that every rational root of g of x, which is of the form p over q with the greatest common divisor of p and q equal to 1, it must satisfy that p divides 1 and q divides 2. So p must be equal to plus or minus 1 and q must be equal to plus or minus 1 or plus or minus 2. And so the only possibility for the rational roots of g of x are plus or minus 1 and plus or minus 1 over 2. So the only possibilities are p divided by q. And we can check each one of them. And by checking each 4 of these possibilities, we see that only 1 over 2 is a root. And so the complete factorization of f of x over the rationals, we know that it has exactly one rational root, 1 over 2. And so f of x must be equal to x minus 1 over 2 times a quadratic polynomial, which can be determined, for example, by dividing this polynomial here, f of x, by x minus 1 over 2. So let's prove this theorem. So let's suppose that p over q is a root of f, and then what we know is that a0 plus a1 p over q plus ... plus an p to the n over q to the n is equal to 0. And so, by multiplying both sides by q to the n, we get the following equality. Now, of course, q divides the right-hand side, so it must divide the left-hand side. And since q appears in every term apart from the last one, it must be the case that it divides an times p to the n as well. Because it divides all the other terms, it divides 0, so it must divide an times p to the n. But p and q are coprime, So by Euclid's lemma, or rather the generalized Euclid's lemma, we have that Q divides AN. So this was one part of the theorem. The other part is to show that P divides A0. But by similar reasoning, P must divide A0 times Q to the N. And by Euclid's lemma, P must divide A0, as P and Q are coprime. Okay, so let us now move on to quartic polynomials. Again, we know that real and complex quartic polynomials are reducible, and there is a quartic formula that can be used to determine the unique factorization, but again, we will only discuss special cases. One such special case is biquadratic polynomials. These are quartic polynomials of the following form. So, the coefficients of x to the 3 and x are equal to 0, and we only have the form ax to the 4 plus bx squared plus c. And this can be completely factorized by applying the quadratic formula. Let's see an example. Suppose we have the polynomial x to the 4 minus 5x squared plus 6. We can now use the quadratic formula, or just by inspection, to factorize the polynomial y squared minus 5y plus 6. This factorizes as y minus 2 times y minus 3. So this polynomial f of x factorizes as x squared minus 2 times x squared minus 3. And now we can further factorize it as x minus root 2, x plus root 2, x minus root 3, and x plus square root of 3. Now let's have a look at quartic polynomials over the rationals. Of course, if they have a rational root, then they definitely factorize as a product of a linear and a cubic, and we can then check whether the cubic polynomial factorizes any further or not. But it is no longer the case that a quartic polynomial over Q factorizes if and only if it has a rational root, as it was the case for cubic polynomials. So for example, if we take the polynomial x to the 4 plus x squared plus 1 over the rationals, then this has no rational roots. It can be checked by the rational root test, but it factorizes over the rationals. It can be checked that this is a factorization, which actually is a complete factorization. So if we just check that this polynomial has no rational roots, this is no longer sufficient to show that it doesn't factorize. And here is an example which actually it doesn't have rational roots, but it factorizes. The final type of polynomials we are going to discuss are polynomials of the form x to the n plus a. And we are going to show how to completely factorize them over the reals and over the complex numbers. Factorizing them over the rationals can sometimes be deduced from the factorizations over the reals and over the complex numbers, but some other times factorization over rationals is more complicated. So let's start from the solutions of the equation x to the n equals 1. These are known as the nth roots of unity. And these are 1, omega n squared, all the way up to omega n to the n minus 1, where omega n is e to the 2 pi I over n, which is the cosine of 2 pi over n, plus I times the sine of 2 pi over n. So the roots are the powers of this special complex number, which we denote by omega n. And in particular, each root is of the form omega n to the k, which is of course e to the 2k pi I over n, which is equal to the cosine of 2k pi over n, plus I times the sine of 2k pi over n. These complex numbers form the vertices of a regular polygon on n vertices, as shown in the following diagram for the case n equals 7. So we have 1, omega to the 7, omega to the 7 squared, omega to the 7 cubed, and so on. And this is always the case for every n. Okay, and since we know the complex roots, we can immediately get the complete factorization of x to the n minus 1 over the complex numbers. This is x minus 1 times x minus omega n times x minus omega n squared, all the way up to x minus omega n to the n minus 1. So this is the product from k equals 0 to n minus 1, actually, not to n, of x minus e to the 2 pi I k over n. So for k equals 0, we have x minus 1. For k equals 1, we have x minus e to the 2 pi I over n, i.e. x minus omega n to the power of 1. For k equals 2, we will have x minus omega n squared, and so on. Now for the complete factorization over the reals, the main observation is that omega n to the k and omega n to the n minus k are complex conjugates. Let's check this. The complex conjugate of omega n to the k, which is equal to e to the 2 pi I k over n, its complex conjugate is e to the minus 2 pi I k over n. And multiplying by e to the 2 pi I, which is equal to 1, we get that this is equal to e to the 2 pi I times n minus k divided by n. But this is exactly omega n to the power of n minus k. And what we will do now, we multiply x minus omega n to the k with x minus omega n to the n minus k, which is equal to omega n to the k conjugate. And this is x minus the sum of omega n to the k and its complex conjugate, plus the product of omega n to the k and its complex conjugate. But the sum of a complex number and its conjugate is twice its real part. So it's twice the cosine of 2 pi k over n. And the product of a complex number with its conjugate is the sum of the square of its real part and its imaginary part. But because for omega n to the k, it's two cosines, it's cosine of 2k pi over n and sine of 2k pi over n, the sum of the two squares is equal to 1. Now, this polynomial here is a real polynomial. And so, it is a factor of the polynomial we were interested in. And by grouping pairs of complex conjugate roots together, we can determine the complete factorization over the reals as well. So let's see an example. When n equals 6, we group omega 6 with omega 6 to the 5, which is 6 minus 1. We get x squared minus 2 cosine of 2 pi over 6 x plus 1. And for cosine of 2 pi over 6, we know that it's 1/2. So we get x squared minus x plus 1. Now we group omega 6 squared with omega 6 to the 4, which is 6 minus 2. We get x squared minus 2 cosine of 4 pi over 6. And cosine of 4 pi over 6 is minus 1/2. So we get x squared plus x plus 1. And finally, x minus omega 6 cubed is x plus 1. So the complete factorization of x to the 6 minus 1 over the reals, so it's x minus 1. For omega 6 and omega 6 to the 5, we get x squared minus x plus 1 here. For omega 6 squared and for omega 6 to the 4, we get the x squared plus x plus 1 here. And finally, for omega 6 cubed, we get x plus 1. And we covered everything, and these two polynomials don't factorize any further because its roots are complex numbers which are not reals. Now, if we have a polynomial of the form x to the n plus a, and we determine one complex root alpha of f of x, then the complete factorization of f of x over the complex numbers is x minus alpha times x minus alpha times omega n, all the way up to x minus alpha times omega n to the power of n minus 1. So it's a product of the x minus alpha times omega n to the k, where k runs from 0 all the way up to n minus 1, not n. So for example, for x cubed minus 8, we immediately observe that 2 is a root, and so the complete factorization over the complex numbers is x minus 2 omega 3, x minus 2 omega 3 squared, and because omega 3 is cosine of 2 pi over 3 plus I sine of 2 pi over 3, we can determine it x minus 2 omega 3 actually is x plus 1 minus I square root of 3, and x minus 2 omega 3 squared is x plus 1 plus I square root of 3. And for the complete factorization over the reals, we need to multiply these two, and we get x minus 2 x squared plus 2x plus 4.